Welcome back to Demystify Sci. Today on the show we have Dr. Raj Gupta from the University of Ottawa, and this is his second appearance on the show. He has a new paper out that claims no need for dark matter in cosmology, which is really exciting to us because dark matter has always appeared as some sort of provisional solution to various problems we see with the motion of celestial bodies through our telescopes. So we're really interested in finding out more about his particular solution set. And without giving the entire thing away, he basically tries to rescue some elements of the steady state universe proponents who had this idea of tired light, that the light could, bleed off energy as it travels across these vast regions of space, and that might account for some part of the redshift that we traditionally account to expansion, some of the clumpiness of the universe that we attribute to dark matter and dark energy. And he thinks he has a solution. The other interesting thing is that it makes the universe older than we formerly believed that it was. So the Big Bang is on the move. This might come to the rescue for some of the anomalous James Webb data, which is suggesting galaxies forming far too fast. And so it's a really interesting topic for us. And we think that this is probably not the last appearance of Raj on our show. He's working on all sorts of other cool topics that we're hoping to get into in the future.
If you like what we do, support the podcast by coming over to patreon.com. We survive solely on patron donations, so huge thank you to everybody who supports us. It is absolutely incredible to have a community of people who value the work that we're doing and show their appreciation by helping us fund it. This prevents us from getting sponsors, from having to put advertising on the show, and if you have a couple dollars to spare to shave off your paycheck every month, we would love to see you. In return, we send you both of the episodes of the week early. You get them on Saturdays instead of waiting for the same day that everybody else gets them. And you also get to join our weekly patron chat, which I personally think is the best thing on the internet. We get together, we talk, we share about the questions that we have about the universe and try to get to the bottom of things. And so we'd love to see you at patreon.com/demystifysci.
So enjoy the conversation, and we'll see you next time.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
So we don't throw out a model just because some new thing happened. Okay, and the age of the universe factor is, people talk about the age of the universe, really it is the outcome of a model which we try to fit to the observation. It is a byproduct.
Right.
And one shouldn't hang on that and say that is right or wrong. Yes, it could be right or wrong, but it's just, what is the evidence? There are a lot of evidence which are related to 13.8 gigayears they have. But before that happened, we remember what people were talking about. The age of the universe started at 2 billion years.
When was that?
Time. Well, that was when Hubble made his first observations about the recession of the galaxies. The Hubble constant has a value about 10 times, or not 10 times, but about 6-7 times of the current value.
So the expansion rate for folks
expansion rate was very fast. So the age of the universe was less. And even before the Hubble Space Telescope was launched, it was people considered between 7 and 20 billion years. Now the lambda CDM model, which introduced the fact lambda. Before that, lambda was discarded. Einstein discarded it, the cosmological constant.
So for folks who are listening, the lambda CDM model just stands for the lambda cold dark matter. This is the standard. I think it's pretty much the standard at this point in cosmology, right? For the timeline of the unfolding of the universe.
That's correct.
And what is lambda for people?
Lambda is the constant which was introduced by Einstein and later despised by him equally. Lambda was the thing which was there to prevent the universe from collapsing under its own gravity.
So it's like a number you have to insert into these equations so that things don't fall apart.
That's right. To ad hoc insertion of a constant to prevent the collapse of the universe. But then it was discarded, and steady state universe was something which was seriously considered. But when the Hubble telescope was launched, then it could see deeper and very large redshift galaxies were observed, and then it became very clear that the universe is expanding faster and faster. So the expansion of the universe was accelerating rather than decelerating, which was originally predicted. Then they have to bring back this lambda or cosmological constant, which then salvaged the original model. So this is why we call it lambda. Cold dark matter with dark matter, where from dark matter comes, dark matter could be hot dark matter, very relativistic particles running around which cannot be seen or whatever, or could be a really very low temperature matter which is not observed. So I think that's another thing we can talk about if you want to go into detail of that. But
Yeah, I do want to get into that. Did you have something?
Well, I was going to ask about the basis of evidence for expansion. Is it just the redshift, primarily?
I think supernovae data, observation of supernovae data, that's when they think that can only be explained by expansion of the universe. Redshift itself points out that the galaxies are receding from us. And if all galaxies are receding from each other, then there must be expansion of the universe. Now, whether the expansion of the universe is accelerating or decelerating, that was in question. And that could not be decided until we have more observations on the more distant galaxies.
And just again for people listening at home, this supernova business is treating different types of supernova essentially as standard candles, right? So
That's correct.
The idea is if you see a car coming at you down the street, it's very difficult, this is at night of course, it's very difficult looking into the headlights to tell whether it's a really big car or whether it's far away. And so by looking at these headlights in our neighborhood and studying them, we can extrapolate out to further away galaxies, take a look at those, and then extrapolate the distance backwards. But what's interesting about all of these is that you are the further away you get in distance, the more assumptions you're built upon at some point, right? I remember originally, I think it was in the 50s, I can't remember who the scientist was, but they had mistaken two types of variable stars for one another that they were using as part of their standard candle system, and they ended up having to double the distance of everything all of a sudden. And so this kind of thing does happen. So just a word of caution that, these things can change. They have in the past.
That's right. This is why one has to have what they call distance ladder. You start from the parallax measurements of stars which are nearby, and then you use that method to really go to the next ladder. Cephids, for example, Cephids have their intensity varies, and variation, the period of variation really determines in a way what their brightness might be, and from that brightness then they can determine what the distance might be, and so on.
That was Walter Beatty. I just remembered Walter Beatty. I think.
But so with progressively distant supernova, there has to be an assumption that all the supernova are the same, or that there's some way of being able to say that a supernova that's far away can be directly compared to one that's closer to then give specific data about distance and expansion?
Yes, to some extent that's true. But really, the light curves of supernovae determine their brightness. So they think based on the information they have. Once they see what the light curve are, then they can be calibrated to determine the distance. They are not the same. All the brightnesses are different, but the light curves can be related to their brightness. And the
So the
brightness
way that
thing
it
can
dims over time, right? So the supernova is very bright, and then it
Mhm.
sort of dims, right? And so the time scale that dims over is what's related. But it does
Yes.
still leave open the door that okay, you have like assuming these distances are correct. Uh, what is the means by which you see these differences as the light travels across eons and eons of time, right? Do you have, and this was a proponent, you mentioned the steady state theorists, Hoyle and so forth. These people were really looking for some way that light could perhaps lose energy as it traveled. Maybe the signal would appear differently, so there might be an explanation besides expansion. And to my knowledge, they never came up with a satisfactory explanation for that really, that people really bought into by and large. And so eventually ceded to the idea of this sole remaining explanation, which was expansion. And that's why we're left with expansion. But what's interesting about that is you bring in some of these tired light ideas into your reconception of the universe, but you still think there's expansion.
Indeed, because tired light on itself cannot explain the various observations. Whereas if we have tired light as a small component of the total redshift, and not you don't determine how small it is. It is automatically determined by comparing the distances traveled, because distance traveled by light is the same whether it is expanding universe or it is a tired light universe. So you can write the equations for the two and then compare those one in the limit of very small distance, and from that you can find what is the relationship between how much is the tired light component and how much is the expansion universe component. Many people think, oh, must have introduced another free parameter to find what the ratio of the two is. No, not only that, it is changing. It is not the same. For early universes, contribution was extremely small, in the range of about less than 1%. In the current universe, at present stage, it is about 20%. So it is evolving. You can't just fix it at one value. And this evolution of the ratio is happening automatically. I'm not determining it. It is determined by the equations.
Is it determined by models for galaxy formation?
No, no, they
Okay,
are
so
not determined by the galaxy formation model. They are just the cosmological model, the expansion of the universe, as I said. Whether it is the expanding universe or it is the tired light universe or both, the distance covered is the same.
I got that. I'm just trying to.
They can equate those two distances, and that's the way you can relate it. You can write the formula if it is only the tired light. You can write the formula if it is only the expansion of the universe, and then you equate these things, and then those parameters which are involved on both, they become related to each other by this equation, equating these two.
And so, in terms of determining the historical evolutionary change in the universe, do we have a sense of robustness for our predictions for the way that the past looked? Is there a chance that our sense of the early universe not being correct?
Up to now, this is what is being proven. As we get more and more powerful telescopes, either on the ground or in the space, we find the predictions we made are incorrect. And this is, as Brian Keating said at many points, that's the beauty of science. If everything corroborates, then science cannot advance. You already know everything. Once we find something which is not fitting the existing knowledge of science, that's where science advances. So yes, there is not, there are a lot of things which are happening we don't understand.
And why is it that you can't equate all of the expansion, the perceived expansion, to tired light? You say that it's only a component.
No, the expansion and twilight, they are two different causes of the redshift. So that's if we say expansion of the universe, then we have to say, okay, most people, that's what it was said before, either you expand expansion of the universe or the twilight, not both.
And you've
Okay,
proposed
so
that it's both in combination
By comparing the
that's
two
right.
models
by
to each
comparing the
other.
two models. And so
That's right.
one thing that I have heard about the supernova light curves before, but I've never totally understood how it is that they demonstrate expansion.
They demonstrate distance with them.
They demonstrate distance, and then the distance is equated with the ones that are farther away being farther than expected. This is I'm missing some piece of this mechanism.
See, if you know the brightness, I think you gave Michael, you gave an example of the headlights. If you assume all cars are same size and they have the same brightness of the headlights, then from the perception of what you are seeing, the brightness of them, you can, and I think car may not be the right example. Think of a motorbike. You don't know how it's far. You can size. If the size of the headlight is the same, and the distance will tell you what how big it should look, what the angular size it should have. That can give you an idea of the distance. The same thing about supernovae. If we know what is the brightness is, if whether we determine it from light curves, dimming of their brightness over time, or whatever what the brightness is, if we know that, then we, by observing, that is the intrinsic brightness. What you see is what you observed, the brightness, what is reaching your eyes. By comparing the two, and by using if it is in the very close by universe, you can use the inverse square law. If it is far off universe, you cannot use a simple unit square.
I think we understand that. I think Nasia understands the distance. I think she's trying to understand how you go from distance to expansion with supernova data alone.
Mm-hmm.
Okay, the supernova data from the expansion, because how you go from there is that you have to see, you have redshift and you have distance. Redshift is one measure of distance, and brightness is another measure of distance. You correlate the two, and that's why it is that distance measured by two methods. Now they should correlate, and that's where the theory brings in. What theory correlates them properly? And that's the theory which gives you then the expansion of the universe, or accelerated expansion of the universe, that comes out of the theory itself. There are also cosmographic methods, which again are not very model dependent. They have tried to find that whether they corroborate with these findings, and they do. And this is, I'm not expert in cosmographic things, so I am not going to comment a whole lot on that. But really, these things, various findings, corroborate this lambda CDM model, which then really leads to the expansion of the universe.
And do we have a sense for what it means for the universe to expand? I know that these are really basic questions, but I want to understand them better, because it seems to me that I don't have a good mental picture of what it means for the universe to expand. Things are just getting farther apart from each other. Space is being created. It's just, it's in the most simplest way, just everything is getting farther away from everything else.
That's right. That's true. That's what is happening in this model. But many models say, yeah, it is going to expand forever, and then eventually nothing will exist. Essentially, they will be so far apart you won't be able to communicate with anything. All particles will fall apart. But there are others which say that might not happen forever. It might reverse over time, and then it might start collapsing again. You know.
I
But
guess I feel like we still didn't answer your first question though, that I am interested in, which is so the supernova data just gives you distances which correlate to the same galaxies that give you redshift data, so you can be sure that your redshift data is at the proper distance. How do we know? It seems like that model assumes expansion in the first place. Am I incorrect about that? What happens if you treat
No.
the model without expansion?
Okay. It doesn't assume the expansion in the first place. Expansion comes from fitting the data with a model, and the numbers which fit the model show that it is expanding. So we call the expansion factor, which is Q0 or something, the deceleration or acceleration parameter. It is derived by, so what
By
happens?
fitting the redshift data? But you're assuming
redshift versus the distance modulus data or brightness.
But I guess what I'm trying to say is that assumes that the redshift is exclusively due to recession velocity.
That's true. That's true. It is allocated to that only, and what have been done then, we assume general relativity is correct. Okay, this is one thing. And then Einstein equations are then taken to fit the data, which is called Einstein equation in the form of cosmology, or called Friedman equations. These are then fitted with the supernovae data and whatever other data, Cepheid data, whatever, and they then find from there that the value which comes out for this cosmological constant is such that it causes the expansion of the universe. It's called dark energy. The lambda, which relates to the dark energy. Not only that, this is the dark energy which is causing the expansion, and not only that, the other part, which is dark matter, which also comes from there, because the dark matter is due to the energy density of the universe, which comes out from this equation, is too high to be explained by the standard matter alone. So there are two types of that. There are two parts of that. One is the cosmological dark matter, and one is the astrophysical dark matter. Then we see in cosmology, we see this dark matter, and then astrophysically, which is rotation curve of galaxies, the galaxies masses, galaxy cluster masses, gravitational lensing effect, all these appears to show there's some hidden mass, gravitational mass, which is there.
But you don't think so.
See, this is why I'm saying it is the equations which they have used that leads to this conclusion. This cosmologically, we find there's a dark energy and dark matter. Okay, that explains the observations. Now, there could be another way of seeing. Can we define the same equation in a different way? What if the one is the energy is being created, which is really repelling the galaxies from each other. Another thing can be, what can be repelling the galaxies? If the forces of nature are weakening with time. If they are weakening with time, that will be equivalent to reduce attractive forces between the, say, gravitational constant being the most significant one here. If that is weakening, that will also cause the accelerated expansion. Now, so if we allow that in the Einstein's equations, then you don't need lambda. And when we allow the twilight to come in there as well, we don't need there's no room for a dark matter. And that's what we have shown, not only by fitting the James Webb data, not only by fitting the supernova data, but also fitting the sound horizon data from Planck satellite, as well as the observation on the distribution of the galaxies in the nearby universe, you might say. Nearby means within about 8 to 10 billion years, light years distance.
So let's take the example people are probably most familiar with, which is the galactic rotation problem, which is often, at least in intro textbooks, is taught as why we need dark matter, because the galaxy isn't rotating like a solar system where the inner things go really fast and the outer things go really slow. It's more homogeneous than that. So they plug in all of this missing material out at the outer limb of the galaxy. How does your model work around that without dark matter?
Yeah. See, this is why I say there are two parts of dark matter and dark energy. One is the cosmological side of dark matter. Another is the astrophysical side of the dark matter. What we have shown that cosmologically it is not required. We don't say astrophysically it is not required.
Mm.
And cosmologically, how much it is required is given by these equations, that we required it at a level of about 25 to 30% of total energy density of the universe, or the matter itself, about 85% of the matter is the dark matter, according to cosmology. And then they try to explain by all the methods, whatever they have. Suppose they go into particle physics and try to find out, is there a dark matter particle? But that dark matter particle should be substantial. It has to be give high enough contribution to the dark matter, that which can constitute up to 85% of the cosmological dark matter. I think this is where the conflict comes in. They find many places they need dark matter. They can explain some of the dark matter. Some galaxies have no dark matter. Some galaxies they have observing have no rotation curves, are very Keplerian at high Z values. The galaxy rotation curves are. So I think the matter is not settled. There is definitely dark matter required to explain the galaxy rotation curves. There have been certain suggestions, retarded gravitational theory, and the acceleration, modified Newtonian dynamics theories, modified entropy theory. There are so many of these which are explaining the astrophysical side of it. But astrophysical side, you can explain. How about the cosmological side? Up to now, nobody was able to explain the cosmological side. We say cosmology doesn't require either. So now those models which are proposing, or those theories which have been proposing alternative to the astrophysical dark matter, they get some credence or some importance.
So, do you think it's just a matter of time before somebody does away with dark matter in the astrophysical side of things? It seems like such a provisional concept, It's like, it seems like you say, okay, if we have dark matter, we can explain this or that, but it's kind of like you're asking for a miracle too. You're saying, well, if you just allow this parameter to sit here and be this mysterious magical substance, then we can end up with an explanation for what's happening. But it seems very provisional to me.
Yeah, this is why there's a lot of research going on particle physics side, Large Hadron Collider, and everywhere they are trying to see for this particles or dark matter particles. In space, they have research going on ground we have, and Earth we have a lot of research going on. And after spending billions and billions of dollars, they haven't found any serious candidate for this kind of thing. Although some people say neutrinos are dark matter in a way. But then we have to find out how you can have so many neutrinos contained to create halos and all those things, how to really make them work the way they are supposed to work in explaining the astrophysical observations. So I think this is not a settled case. So we definitely feel that dark matter is and dark energy both. They are very elusive, and satellites have been launched to really do research on those. And the daisy research out of Arizona telescope there is dedicated for this dark energy kind of thing. So both dark energy and dark matter, they are complementary in a way. If you remove dark energy, then to me dark matter automatically disappears. Some people may not agree with that, but to me it seems their dark energy came in these equations. Then we say, okay, now so much is dark energy, remaining is the energy due to matter, and that energy due to matter is not cannot be explained by the standard matter which we understand. That's why there must be dark matter. That is the cosmological side of that.
Yeah, it makes me think if the real revolution will come, and this is to some extent what you're doing, but by shifting our perspective a bit, it reminds me a lot of the caloric theory of heat, right? They used to believe heat was a fluid that flowed through substances and gave them their warmth, right? But then they discovered that they couldn't detect this substance no matter how hard they looked. And in fact, it seemed to be inexhaustible, right? When you're boring out, drilling out a cannon, you can create endless quantities of this magical substance. And it turned out that by looking at it very differently, by thinking, wait a second, what if this is just a process that atoms are doing, an activity of atoms? It has to do with the actual vibration of the molecules. What if that could explain it? And it turned out to actually work just as well, if not better. So, and for more applications. And I wonder if dark matter won't suffer a similar, I was going to say fate, but if it won't suffer a similar triumph, where there's a different way of looking at what's happening in terms of the actions of really the celestial bodies or the atoms that are involved in terms of producing this effect. What if it's not just a gravitational phenomenon? What if we're looking for something totally in the next room compared to what we're looking at right now?
Yeah, I think I have another example is if you recall, luminiferous ether, which was explained for the light waves to travel. Light, right from the time of Newton, who didn't agree with the wave theory of light, but even for explaining the birefringence and similar effects of light, we had to invoke the wave nature. And waves, they couldn't see how they can propagate without some kind of medium. Even Maxwell, I mean, all the scientists of 200 years from the time of Newton to Einstein, until the time of Einstein, they believed that ether is essential to the theory. So that existed for a long time until it was debunked. So I think it may not, this may be the fate for dark matter and dark energy or whatever. But really, to me, until that happens, it is still helping us understand the science around us. So we can't really debunk something until we have something much better and proven in different aspects.
With dark matter, I've always wondered, or dark energy, I've always wondered if it isn't just a problem of not being able to see something, right? Because at a certain distance, you're looking at objects that might be cold, that aren't fusing, that might not be magnetically active. Is it possible that the anomalous...
It's actually a theory for this. I think it's called Rambo's, which... I'll have to look up the acronym, but there's this idea that perhaps some of this could be due to cold, dead stuff. But I think the conclusion was that the universe hadn't been around long enough to generate that much cold, dead stuff.
Sure, but as we begin to expand the age of the universe, are we not expanding the possibility that the universe has generated enough cold, dark stuff that could be dark matter, which would neatly explain why we can't find dark matter in any of our particle detectors.
I think I like the other idea, which Michael proposed, that there's something right in the next room we don't understand. And this is why we are trying to say that it is the gravitational effect of dark matter which is causing these astrophysical phenomena. As I said, the cosmological side of it can be taken care by this kind of approach which I have suggested. The astrophysical side, it might be a little bit tricky, but at the same time, once people know that we don't need in cosmology, then the strength can be given to alternative theories. And there are several theories. I have been in contact with some of these authors of these theories that they can explain everything without the cold dark matter. Gravitational lensing, they can explain the rotational curves, they can explain the cluster masses, all these things which are attributed to dark matter can be explained. Plus, a lot of places dark matter don't exist. And not only that, in my coming paper, I have shown that dark matter is not required for forming galaxies. Why? Previously, they thought you cannot even form the galaxies without dark matter. Because dark matter provides the potential well for the normal matter to really get into a stage of galaxies that we see. But if we have a lot more time available for forming the galaxies, you don't need the assistance of dark matter in forming galaxies. This is what I have tried to show
I like
in
that.
my forthcoming paper. And not it's not the twice the age. Twice is the age which we calculate the total age. But in early times, the age proportion was more than 100. If you go to the at the time of redshift, when it was in the range of 1000, when cosmic microwave background, this ratio was more than 100 times the standard model. So you have a lot more time to form the galaxy. Then people will say, okay, but if you have less mass, then the free fall time of the mass in the gravitational potential well will increase as well. And their cooling time will increase. That's what I have showed, that combination of these two increased in time is much less than the gain in the age of the universe at that stage. That
How,
means there are a lot more time for forming the galaxies.
so how do you relate that to the galaxies that have been identified by the James Webb at the very edge of the universe that seem like they formed much faster than current models suggest?
Yeah, according to, if you have only 13.8 gigayears or billion years of lifetime of the universe, you have to form them very quickly. And in my first paper, which was in last July, this is what I showed. Either you form them more quickly or you stretch the time to form the galaxy. I didn't stretch the time. I just fit the data, and it happens to come out to be that much time. And that's what created a little bit of buzz about the age of the universe. I didn't try to create the age of the universe that much. It means lambda CDM model, for example, when it gives the age of the universe to be 13.8, it is not that somebody is trying to fit 13.8 there. It is the model which gives it. And then they try to see with that model, can they fit the astrophysical observations, like the age of the stars and all those kind of things. And what they did, age of the stars used to come out quite high. But they had to adjust those things, because if cosmology says you have only so much time, then your stars cannot be older than the universe. So you then adjust your models to parameters in the model so that it remains within 13.8 gigayears. This has been done all the time. And even now, that's what I should cite something. I should say something. One of the author, whose paper is just recently published, after he had done some calculation in which he was getting this stellar age to be close to 20 billion years. And he said, oh, I was going to discard it, that this is not possible. This is totally rubbish. Then he saw my paper and he thought, yeah, there is a hope. Maybe I am not so wrong. Why to discard this model? So he published that paper because now there's more room for the age of the stars. They can be quite a bit higher than 13.8 gigayears.
And how is the age of a star determined? Just by location?
No. Age of star is the formation. How do you form? It depends on the size of the mass of the star, size of the mass, and they together how they collapse in nuclear reaction, burning of the helium, hydrogen, then eventually helium burning, carbon burning, all these kind of thing process it goes through, and then you determine what the age is. This is itself. It can take some time to explain it in great detail. I don't think you want it to be
Based on models
that much
models
detail.
of star life and death.
Well, basically, like
Yeah.
the amount of time that it takes to get that amount of material into one place and behaving the way that it is observed to behave, you can do a back
And cook it down.
and cook it down. You can do a calculation.
For example, sun has a total lifespan expected to be about 10 billion years. It had gone through about 5 billion years of its life up to now. So that is based on, of course, they are based on certain models, how the fusion takes place, how the collapse takes place, how you release the radiation energy into the space, all those things together, And not only that, larger the size of the star, smaller is the age of the age of that star. This is
The
and
big
some
ones
of
burn
the very
themselves
very
out
large.
quicker.
I'm sorry.
The big ones burn themselves out quicker, right?
Very quickly, yeah, very quickly, yeah. It can be instead of 10 billion years, it could be 10, 20 million years only for some of the largest stars.
And so, as we adjust the age of the universe as it falls out from these parameters, do you think that it changes anything for us as humans? Because cosmology was always a very theological pursuit. Prior to its transformation into a science in the mid-20th century, it was the domain of the church to talk about the cosmos and our position in it. And so, as someone who is studying something that has such deep spiritual overtones, do you find that changing the age of the universe changes anything meaningful on a human level as opposed to just a scientific one?
I don't think it should be, but still somehow the age of the universe and the secrets of the universe, whatever we talk about it and we change, something changes there, then it excites everybody and gathers the attention of a lot of people. Although in our tiny speck in the universe and even tinier time scale on which the intelligent life exists in this universe, I think it's perhaps insignificant. But mind is mind. I mean, we think in theologically when we think, and things around us theologically change, then we think we are affected, even though we may not be directly affected. So I don't know. It's difficult to answer that question.
Well, I mean, it seems like at the heart of all of this is a very supernatural proposal that matter and everything we know just came into existence one day. Like that's a crazy idea, right? I mean, from if I was to try to propose that solution to why my cell was behaving the way it was, it just something came into existence, like it just a nucleus just appeared, no material added. It just like it's a very very mystical heart of this science. Would you agree with that? I mean, this idea that there's a birth of existence itself is just so, it's quasi-religious to me, right?
I think yes, but I think no matter what we say, whether universe started from a Big Bang or it existed forever, we still have those questions. If it existed forever, even then we think, if people say you are asking a stupid question if you say that what was before the infinite universe in infinite time. I mean, if something is infinite, then there's nothing beyond infinite anyway. So, but at the same time, it is whether we say it began from a Big Bang or it always existed, still both questions are equally fascinating, or answers are equally difficult to frame.
Yeah, they're both really hard to imagine. Either one will break your brain if you sit down and really think about it too hard. I suppose the difference is just that in the case of the Big Bang, you propose an event that is singular, right? We can't study Big Bangs in a laboratory. There's no way to.
Can we study eternity in the laboratory?
Well,
this is the problem when you start to talk about the origin
it's
of the
not an
universe,
event,
is
right?
that it is the lack of an event, which makes it even more difficult, because at least if you say that it's the Big Bang and you can boot up a particle collider and you can say that you've gotten enough energies to approximate something that reflects something that's Big Bang-y, then at least you're purporting to study something experimental. But to say that you study the lack of an event, I think that
we can't study that, for starters.
well, you can't study a lack of it, exactly. And so it immediately puts cosmology into the realm of philosophy, right? Like, if cosmology is to be a scientific discipline, it must have an event to study. And if the event is eternity,
I guess Fred Hoyle tried, right? So maybe we could go back to Fred. Have you read Fred Hoyle's work on tired light?
Yes.
Could you tell us a little bit about that, and maybe tell us where you think he went off the rails or what he got wrong? I mean, I know he was famously very disappointed that he wasn't able to solve this problem, and so I'd love to hear a little bit about that. I've tried to read his writing; it's impenetrable. So maybe
I don't think I can go so deep into that. All I can say that his most celebrated theory was the continuous creation of matter in the universe, and that is a steady state thing, that the matter is continuously being created and instead it's not very different than energy continuously being created in the lambda CDM model, because in that one also energy density remains constant. The dark energy density remains. Density constant mean in expanding universe, you are creating energy out of nothing. So whether you are creating energy or you are creating particles, they are the same in that way. Whether they expand, now, is the universe expanding or not expanding? That is another thing. And in that way, what they call quasi-steady state theory, that in the Fred Hoyle's and Nordical theory, that one is that universe is expanding, but is filled by new matter at the same time. So it is what they call perfect cosmological principle. That means it is not the cosmological principle, this is isotropic and homogeneous and the same everywhere, but it is same everywhere and every time. So this is the perfect cosmological principle based on, that is the basis of Fred Hoyle's steady state theory. That's what I understand.
Yeah, it's something. If I recall correctly, it's something like the galaxies are spitting out. They're churning something out of their hearts, maybe these active galactic nuclei or something, and it's pushing the galaxies away from each other as these new ones. As the galaxies live out their lives, they kind of spray out these fire hoses that push them away. So you get this appearance of expansion. But in the interceding regions, you actually have the collision of these fire hoses and you get the creation. You can create new galaxies this way or something like that. I think that's how it goes.
Yeah, I mean, you are creating the the matter being created all the time. How it is being created, then there are different conjunctures on that. And one of the conjuncture is what you are stating, but there are other which are spontaneously creation of the matter
Like at the heart of the
out of nothing.
galaxies. Is it from in
No,
the
no, it could
jets?
be anywhere it can be anywhere spontaneously,
Huh.
anywhere in the universe. Yeah,
I didn't realize that.
yeah.
Have we covered the blue shift galaxies? Because don't
Like Andromeda?
don't the neighboring blue shift galaxies cast a slightly more complex light on expansion?
Actually, this is called the peculiar velocities, because when you are all the galaxies have some peculiar velocities and then expansion velocity. Peculiar velocities are relative to you. They might be appearing that they are really blue shifted to you. That means they are approaching you. But these blue shifts are extremely small, of only very nearby galaxies. But when you go to far distant galaxies, they might have a component of their velocity which is approaching us, but that component is so small compared to the total expansion of the universe that you don't see for distant velocity. You see that only for nearby velocity, that component.
I think that's at the heart of the expansion proposal, is that the things that are really far away have much bigger, they're moving much faster than things that are closer by, or something like that.
So the redshift just overshadows any component of it that might be towards us.
Yeah, redshift due to expansion or some other method, twilight or something, is overshadowing then the velocities, which are random velocities of the galaxies, part of that. Some of these could be towards us, some could be away from us.
And so when we talked earlier about this idea that perhaps there's something in the other room that we haven't really figured out how to wrap our heads around that could be responsible for all these things that we see that are anomalous, do you ever spend time thinking about what that thing in the other room might be?
Obviously, yes, I do think, but unless it reaches a stage where it is meaningful, which I can make meaning out of it, I don't want to present it to others. But some people have already put those ideas, and I think I'm trying to see whether these ideas can be universally explain the astrophysical size of dark matter. Because it's not that sometime it explains, sometime it doesn't explain. It should be able to explain in every situation. Even dark matter doesn't explain in every situation. In fact, dark matter concept fails miserably in many cases, and then they come back and say, "Oh, this maybe some kind of tidal effect removed the dark matter from this galaxy, but not from that galaxy." The Keplerian curve, which are observed at high z, high redshift, might be due to this reason or that reason. So that dark matter is not really universally able to explain the observed phenomena either.
So this opens another can of worms, which is that a lot of astronomy seems to be based on a kind of uniformitarianism, which is that you look out and you see things that have a similar light curve or similar luminosity or similar behaviors, and you equate between them that they are the same thing, and so are able to construct distance ladders, able to construct these expansion relationships. And I wonder if there's any systemic issues with that. I mean, the discipline can't exist without it. And so it's probably a hard thing to talk about. But I wonder if there's anyone who's thinking about, the applicability of a universal measuring system for something as big and diverse as the universe.
This is one of the big problem in cosmology. While the experiments you can do in the lab, when we wanted to understand smaller and smaller things, so we were able to do in the lab, and eventually we hit the impasse that we can't go any smaller, and Heisenberg uncertainty principles and the size of the particle and quantum nature, all these came out clearly. And we were able to then really pinpoint it because we can do it. They are within our reach, whatever. And we could put the limitation on that. Now, this kind of thing, we cannot do this kind of control experiments in cosmology because we can't really bring that to the lab. So we have to depend entirely on observation and statistics. And this is what we have tried to verify. Various satellites, increasing our observations and finding that statistical relevance, that has provided the strength in the measurements. Like James Webb Telescope itself had been used to firm up the data on the supernovae, standard candles, for example. There were some other uh, observations also work towards confirming this. And up to now, they have not been able to find a reason to doubt that data. And we are not doubting that either. Although there may be some bias in that, when we try to find something, we see within that observation which we have, that is the limitation we have, what other models can explain these observations. Because James Webb observation could not be explained, and even today they are not able to explain very well these galaxy angular size data or at the cosmic dawn. And we think we have been able to explain that.
And the angular size data is that they're fully formed but smaller than expected?
That's right. They are fully formed and smaller than expected. That's true. Thanks for clarification. Yeah, so that kind of thing is not really able to explain, although they are trying to work towards it. They are trying to modify their galaxy formation models to show that it can be done. But more they do it, more they try to fit the data, more observations are obtained, and they are again becomes in conflict with whatever newer models they are able to develop for galaxy formation.
And so what is your solution to this problem?
The solution to the problem is that we have to have the model we have proposed provides a solution that the angular sizes, bringing in the tired light, for example, that gives you the angular sizes as observed without requiring them to be very small in physical size. Physical size could be much larger than what they are saying they should be according to the other model.
Can you elaborate on that a little bit? How does tired light allow you to expand apparent size versus actual size?
This is called angular distance of the objects, angular physical distance. Angular size is one thing. What we observe in the sky is only the angular size. We don't observe the physical size. And physical size then depends on the model, cosmological model you use. And because of the expansion of the universe, rate of expansion of the universe, different models give you different physical size for a given angular size. Now, our model gives a angular size, which is a physical size for the same angular size, which is 10 times approximately larger than what the standard model gives. And then it is not in conflict with the galaxy formation and galaxy evolution. But now, how the galaxy can become so big in very small time? That is not a problem in our model. That is the problem in the other model.
Because since you have a longer time span, the galaxy has enough time to get big. But again, so I think that the standard model says that those galaxies formed in 500 million years. And so if you're suggesting that the universe is twice as old, does that mean that they formed in 1 billion years?
No. They are formed because it is not uniform. Age of the universe is not uniformly increased or doubled. In the early part of the universe, the increase was much, much larger. So what you call 500 million years, at that redshift, if we consider the age of the universe was 5 billion years
I see.
in our case. So you have 5 billion years to form the galaxy, not 500 million years.
Because things are happening
An order
faster?
of magnitude. Sorry?
Just because things are happening faster, or you're talking about some sort of like time dilation effect, or
Not time dilation effect, because of the rate of expansion of the universe is smaller in the new model than in the standard model. So there is no time dilation in that way. But we have more time available for forming the galaxies. But as I said, there's more time available for forming the galaxies, but then the free fall time and the cooling time are also longer. So it's not that we have 10 times more time available. We perhaps have 3 times more time available to form the galaxy than in the standard model.
Because the dynamics of
all
the
the-
molecules.
That's right.
I
The
see, I
dynamics of
see.
molecules and
What accounts for that kind of nonlinearity of things happening faster at the early universe and slower later?
okay. Yeah. The thing is this, if you consider, for example, the redshift itself, redshift of 1 or 2 takes you to about 10 billion years. Redshift of, I don't remember the exact numbers, but this is a very non-linear effect. When you go to redshift of 1000, you have only 380,000 years of the universe which has passed. Redshift of 1 or 2, you have 10 billion years passed. You can see they are very non-linear effects. Similarly, the age itself is a non-linear effect. Age of the universe when you establish. Same kind of non-linearity exists in there too.
so he's saying it's empirical, but you're asking for the cause of it.
Yeah. I'm like, it's measured, but what causes it? What causes the measurement to be so?
Okay, that's something good. For example, okay, let's consider launch of a rocket. It has the same force being applied. Okay, it travels very little distance when it is launched in first 1 second, 2 second, 3rd second, but it keeps increasing very fast. The distance traveled becomes faster and or larger and larger in a second. Similarly, something falling under gravity. Initially, the distance travel is very little, but the acceleration being the same, it covers more and more distance in the same time. Same kind of thing you can see in here. Expansion of the universe, if you take it is happening at certain rate, then it's going to cover the more and more distance and time. And distance is time in cosmology. So it will cover more and more distance in a shorter and shorter time.
It's kind of counterintuitive.
Well, in the case of the rocket, I suppose it's escaping the gravity, right?
Yes, and in the case, so is it the idea that the singularity has this immense gravity, and as it escapes the gravity of the initial singularity, or I understand that gravity is something that emerges later, but there must be some interaction
As
that
the
holds.
particles get farther and farther away from one another.
Oh yeah, like there must be something that holds the thing together. If we take the Big Bang to be the model that we're discussing, at the beginning there must be something that holds all of this matter together. And so as it escapes that, that's the analogy of the rocket escaping the gravity well of the Earth?
The analogy I was giving, not how the Big Bang happens, I was giving why this is a nonlinear effect.
Sure, but the nonlinear effect is the expansion of the universe, and the expansion of the universe
That's right. Expansion of the universe. Suppose you assume the rate of expansion of the universe is the same. For example, if you take the same, but that means in a given time, as the time passes, it will have more and more distance traveled. So separation will increase more and more over time.
Right, that makes sense.
Can we go back to those astrophysical models? You said there might be a few things in the other room that you're not working on, but you said other people, and I think you mentioned the neutrino case. Are there some others that you've heard of that we could maybe follow up on for people proposing alternatives that aren't necessarily gravitational to explain dark matter effects?
You mean from the particle side?
I don't know, from anywhere, from any side. Anybody who's thinking about it outside of the box, I'd be really curious to hear about.
There are various types of particles. One, as Anastasia has proposed, perhaps the dead stars of the past,
Yep.
which might be there and lots of them everywhere, and then they may be causing this so-called dark matter. But that has been explored to a size which is of certain size, up to that extent, through gravitational lensing effect. The events of gravitational lensing, if we can observe that between us and the LMC, Large Magellanic Cloud, for example, that kind of thing, lensing of that stars from such massive objects would give rise to so many of the lensing events, but they have not been observed at that level where it will satisfy the kind of mass we need. Okay, so that has been eliminated, but then they are not eliminated. There are people are still thinking maybe they are smaller ones, but then how they will create
Well, the gravitational lensing thing is kind of weird because you don't see it with every star, right? I mean, we don't see the, like, you look up at the night sky, you don't see lensing everywhere, right?
Actually, lensing is everywhere. If you see at the with the very large telescopes, you will find the lensing effect seen. The Einstein ring arc portion of the arcs is everywhere in these kind of observations. Lots of them.
There are lots of them,
But
but if you look at these wide field images, you don't see it on every single star that's in the foreground. You see it in a lot of them, for sure.
No, that's right. This is why I'm saying that if the gravitational lensing, if such objects which this dense object, or they call it machos, massive, what astrophysical some objects, I forgot what the acronym stands for, but these objects which are massive objects, if they are really the dark matter, then we should be able to see more gravitational lensing than we see. I mean, this has been done, this kind of experiment, and these experiments show not really any significant gravitational lensing for dark matter to contribute significantly.
Do you know the NASA scientist, the late Edward Dowdy, by any chance?
Edward Dowdy.
Yeah, Dowdeye, I think. Anyways, he wrote a really interesting paper where he proposed a mathematical solution to the lensing of light that had nothing to do with gravity, that had to actually do with some sort of plasma reorientation of light through the atmospheres of stars. And I don't know if he's right or not, but it's an interesting case because if it turns out that he's right about that, or in any way right about that, then the lensing might not occur with non-luminous bodies as we would expect.
Yes, but that may be an alternative, but gravitational lensing, as we understand, as proposed by Einstein, is still observed every day.
In some
there
cases,
are cluster of galaxies. No, some cases, but some cases itself tells you that that exists. Now, to what extent it exists depends on how many gravitational lensing objects are there. And one can see from the statistics, one can definitely say, and gravitational lensing doesn't have to be by dark objects only. Gravitational lensing will
No, I was
happen.
talking about light objects. Yeah, I think it's
Like,
only observed in light objects.
yeah, that's right. It is
I mean, I think
not.
that there's a statistical question here, which is that you have multiple things that have to line up, right? So Shaila's pointing to the fact that if you look at a Hubble deep field or the James Webb deep field, I don't know if it's called that, you see gravitational lensing on some galaxies, but not on all galaxies. And one simple explanation for that could be that all galaxies lens, but only some of them have something that's behind them that could be seen as being lensed. You have to have something behind it to lens.
I think a
right?
more salient argument is just that some process is causing the lensing other than gravitation. That's kind of what I'm pointing at.
Yeah. Is it possible that gravitational lensing is not due to gravity, but is due to some other effect of the galaxy? Is anybody looking at that?
Yeah. I would say that it could be other causes as well, because for gravitational lensing, because gravitational lensing, if you see from the perspective of whether gravitational lensing object or lens itself has a dark matter embedded in it or not, then we might say the gravitational lensing, the way we are observing, is not really gravitational lensing as we think it is, but it is something beyond that. Okay, that means all the lensing which we are observing today, due to these galaxy clusters, for example, which are acting as lens, it may not be because of the mass alone. It could be due to some other factors in there, which are some of the people are trying to explain that gravitational lensing is not due to the dark matter hidden in these galaxy clusters, but visible matter plus some other effects.
Yeah, I mean, there's weird, like, if you go, we were just driving through the desert, and when you're driving down these hot desert highways, you see these crazy lensing events off the
Yeah.
road, right? And I couldn't stop thinking about the gravitational lensing thing when we were driving. I was just kind of obsessing about it. And there's arguments made, that it's not, it's very inconsistent. I originally was dissuaded from this idea because the kind of lensing that we see with gravitational lensing is it's not chromatic, right? It affects all of the different wave bands the same. But there's been some interesting reports of it actually being chromatic in some cases and achromatic in other cases. And I just wonder if there's not a better answer that's in the next room, that we're not approaching it. We had this really cool conversation with a scientist who's an astronomer who's beginning to look at the role of galactic magnetic fields in the evolution and the distribution of matter in galaxies and so forth. And, I don't know if that contributes in any way or not, but it seems like there's new fields of inquiry that are creeping in that might have something to say about these matters at some point.
Yeah, I think so. I think there's a more than what meets your eyes here. So to say that solution for everything is dark matter is perhaps incorrect, because we know where in many places dark matter is not there where one expects to have dark matter, and people are able to explain it by simply saying that it has been pulled away by some kind of tidal effect, the collision of galaxies with the galaxies, or some kind of similar effects. So I think the debate is not yet over about this, but all I can say that we are providing a model, cosmology side, which does not need dark matter or dark energy. So now we are free to consider options for dark matter in astrophysics.
Nice. Yeah, I got that. It is. I love what you just said. It could be more than meets the eye, and that's the strange thing about astronomy, astrophysics, cosmology that makes them very different from other sciences. Because all you have is what you see. In this case, you only have light, right? That's That's pretty much it when it comes to looking at the sky. And we
More
can't
than that,
put
we
the
are
stars
getting,
in test tubes and compare them to controlled, in controlled experiments, right?
yeah, there's something more than now light which is being used is what you call gravitational waves, for example. So there is multi-messenger neutrino, for example, is another neutrino astronomy is also getting some traction. So there are other things, but they are very in a very early stages of being called a precision uh, cosmology uh, probe, because only the electromagnetic waves, whether they are radio or visible or whatever, they are the high precision cosmology probes. Others are still in very early stages,
I think
but
that
they are coming. They are coming.
like when we start talking about the electromagnetic radiation coming off of a galaxy being able to change the path of light, you immediately run into the problem that you can't have, as far as I understand it, a magnetic field without also having a gravitational one. And so how do you tease apart the effects of something that comes from gravity versus something that comes from something else? Because the gravity is there from the massive object in the first place.
And the gravity is much easier to study, right? Because you need, the only way you can study magnetism is through polarization of light.
Mm-hmm.
And you have to sort of hope that's accounting for what you're seeing. The problem is these galaxies, from what I understand about the magnetic field mapping, it's not clean, right? There's different field orientations and field strengths in different regions of the galaxies, and it kind of gets blurred out with these distant galaxies. So it's very difficult to see an appreciable magnetic field at all with these distant galaxies. And so, yeah, teasing it apart, I think, is going to be a real challenge in the future.
I just always think about the way that, prior to, I think it was the Viking landers that went to Mars, we had this really, really, really inaccurate picture of Mars. We thought that there was perhaps seasons on Mars because there was the yearly darkening of it. And it turns out that there was not a growing season where plants covered it. It was just the shifting of sands. And it required us actually to have something that arrives to the place to look at it, to be able to see what's actually happening. And obviously our telescopes are better now, and today if we point it at Mars, we can see it much better. But the mystery there remains, which is that we have data, and the data allows us to tell a story. But the story is limited, A, by our imagination, and B, by our preconceptions. And so it seems like these may be questions that don't have answers because we can't go to these distant places. You're smiling.
Yeah, I mean, that's the problem with astrophysics and cosmology. We have to depend on observation, and we have to depend on models, and then we have to then corroborate and make sense out of it. So this is the big challenge we have. And somebody asked me one question, that what is what is the next big challenge in physics after the quantum discovery of the last century, around this time, around this about 100 years ago. And my response usually is that, we were able to study in lab something very closely, and quantum mechanics was developed. Cosmology is just the other end of the things, that how big, how to understand the biggest, and combining the two is going to be the biggest challenge. How do we integrate the largest to the smallest? It's the so-called theory of everything, or uniting the gravitational theory with quantum theory, or quantum gravity, or whatever you might like to call. That perhaps is the biggest challenge.
And
Today.
one of the things that I have a sense makes it challenging is the destruction of the ether, right? So if you don't have something that fills the space between objects, then there's no continuity, or there's nothing that extends between objects. Then all of a sudden you have a break in reality, where you have something that is very, very small, and it is discrete from the things that are very, very big. And I feel like the study of astronomy, which is the study of light, forces one to think about how those two can be related. Because the only way that you can study the very big is through light. And so how does our light-based study of the very, very big give us clues to the link between the very small and the very big? Do you have a sense of that? Or is that too mysterious of a question?
But this is where we believe the fields come into picture. We have to consider that every particle is not located where it is. It has fields all over the universe. That's where the entanglement phenomena starts coming in. There are so many other things. Are we really communicate through the speed of light, or do we communicate at higher speed than, or instantly? For example, there was a time people thought the gravity, how the stars or planets rotate around you, there must be infinite speed of interaction between the particle. Newtonian gravity should be traveling infinitely fast in order to explain the observations. And people fail to observe any gravitational, the speed of interaction between the gravitational objects. But then Einstein theory of gravity came, and it says it's nothing to do, it is the gravity is not really what we think. It is because the particle move in the form of geodesic. They follow the geodesics. So he defined by equations that way, and there was no question of interaction, speed of interaction between the particles. So I think we have to see how do we bridge the gap between very small to very large while limiting ourselves with the speed of electromagnetic waves. We have to get out of that paradigm. The electromagnetic waves are not the only thing which connects us. Something beyond that, something else connects us. What that something else is, I think this will be the new physics which we are waiting for.
Do you think that there's a clue in tired light for what that thing might be? Because it seems like if light is traveling across this massive distance and it is, becoming tired, quote unquote, what is that? What causes that?
Yeah, where is it becoming tired? Is it becoming tired when it relays off of another atom? I always think about how it's interesting that when we say this light is traveling from billions of light years away, there's a lot of atoms in between us and it, and many of them would be considered transparent, let's say. Is it losing energy during those transparent relays?
Yeah, if you extend it to that, then you will find that's what original idea was, Compton scattering. Because these transparent things, they don't change anything in the light, as we know. It is the scattering process which might do it. But we don't suggest, in my theory, I don't suggest that the Compton scattering is happening. There's something beyond that. We talk about fluid dynamics, for example, for explaining cosmology. There is some kind of, and people even talk about lossy fluids. So there may be certain things you might say non-conservative fields. If they are non-conservative fields, then particles traveling through such fields will lose energy. So that it is difficult to visualize how it will happen for the light and field per se, given our present knowledge. But definitely this is a possibility. Something like that may be happening for light. And about your thinking that whether tire light could provide a solution for the missing link we are looking for communication, I think I'm not sure if that is where we should look for. We should look for how to explain entanglement, where entanglement really is communicates instantly between two particles.
Well, it seems to imply they're connected to each other, like physically.
And that's right. It implies that it is there, but at the same time, no matter how far away they are, they appears to if you know the state of one, you instantly know the state of the other, no matter how far they are. So there's some kind of entanglement phenomena which we don't understand how it happens. Or we say it is a quantum mechanical effect, and that's we leave it there.
So one thing that I wonder about entanglement is that we've extended the theoretical construct to what is beyond what we've demonstrated. Entanglement has been demonstrated at a maximum of around 300 kilometers. And we extend it to being that any two particles anywhere in the universe would remain entangled. Is that a fair extension of that assumption?
Actually, there have been some experiments done at cosmological scales. How they have quasars taken far apart, and quasars were then these quasars were considered to be completely random. Their light emitted from these should be completely random, and those lights were then controlled the filters in these two entanglement bodies, which were whatever their distances. And they find, despite their control being done by these quasars, which are billions of light years away, the entangled phenomena was still observed. Now, whether it is a proof or not, I have some skepticism about that. In the process of when these lights are coming closer, these beams which are coming, they are collecting those lights which are controlling these filters. When they come very close to each other, are they interacting with each other? And that's why they are having this kind of phenomena. Or so there are always ifs like this. You are right. It is very difficult to see entanglement really is. But at the same time, we know the qubits, which are quantum computers, for example, they are, once they are really practical, they can't work at the speed they would be unless their entangled phenomena is there. Otherwise, they will be still limited with the same kind of limitation which we have on the semiconductor devices.
Mm-hmm.
I may be wrong. I'm just conjecturing it.
I think that you point to something that's really important, which is that we can only experience nature through the detector. The detector can be the eye, the detector can be the experimental apparatus, and we're stuck with the challenge of looking at what the experimental apparatus tells us and asking whether or not we wish to question the experimental apparatus itself or to accept the conclusions that it has put down in front of us. And that seems to be maybe one of the hardest things in these weird physics realms, because I get the sense that we really like the magic of it. You know, if somebody looks at the light that comes from the two quasars and it shows that it's entangled, that's far, far more interesting than saying, well, perhaps the detector on Earth right next to each other is also entangled, and that's where the signal is coming from.
Actually, quasars are not shown to be entangled. All they have done is these quasars the light from these quasars is controlling these filters. which are then showing the entanglement phenomena. So if they control these filters by some local random process, then they might say that are they truly random? But when the light is taken from such distance quasar, they're assuming they're random. So it's not entanglement at that kind of scale. All it is showing is that randomness is not affected by entanglement.
I think we still have a lot to learn about light. There's this classic picture of light just being emitted from one atom, but it doesn't really take in the full picture. Are you familiar with Carver Mead's work with collective electrodynamics or anything like that? I mean, he really does a great job of looking at how both atoms participate in light and how it's actually some sort of conversation between atoms that in some sense begins with both atoms involved. I think this idea was really advanced by G.N. Lewis, the chemist, in the early 20th century. That, hey guys, wait a second, we can't talk about light without two. And I wonder if there's some answers in there. That's why I don't think you should give up on your tired light idea contributing to the answer to this problem, because we see tired sound waves, right? We see tired waves, tired waves in other materials, right? And it tells us something about the material property of that material, right? It tells us about the stiffness or about the density, or it can tell us something, right? So there might be information there.
I think that's why we have this discussion here, that maybe somebody in your audience has some good ideas about what we are not able to think about, And to me, I think this is the best part of when you say demystifying concepts or something, then this is where we try to bring in the new people. Sometimes, younger people listening, when I teach in a class, I present this problem to people, students, and I say, it is your problem to solve when you grow up, for example, or tomorrow. You may have new ideas, you have new brains, so you may have something you can think out of the box, which we can't. So
yeah, that's absolutely the point of what we're trying to do here. We don't have the answers necessarily for most of this stuff. The thing that we're trying to lay bare is that oftentimes something like dark matter or these dark substances and so forth, they sound like solutions to a problem. They have that scientific taste to them. But what they really, and what I'm dedicated to trying to promote here is that they actually are mysteries, right? There's a lot of work to be done in those phenomena. The effects have been kind of transmitted into these magical substances, but the reality is that there's so much more work to be done. And so I do hope that people put all their ideas down in the comments. I'm sure, there's going to be good ones, there's going to be bad ones, but let's hear them, let's hear it out. Let's put our heads together and think about these for the real mysteries that they are.
Yes, indeed.
And so what is next for you? What are you focusing on these days?
My focus, or I should say our focus, is to put few people together to really go and study 3 other major challenges of any new theory. One is we want to have the cosmic microwave background, anisotropy spectrum or power spectrum of that, to see how that fits with the new model. We also want to explain the Big Bang nucleosynthesis, whether this theory passes that test. And then the other one is large structure formations. So that is
like cosmic filaments?
Yes, right. Something like that. That how does this new theory is able to jive with that? Is it really consistent with that? At least as much as the lambda CDM theory is. So we want to see that. And one problem I face is that people have to understand this new theory correctly and in wholesomely, rather than only understand partly just to prove that it is wrong. Because I had somebody who did this kind of thing recently, published a paper in which they just had one part of it taken and showed that it is wrong. And they did not see, they tried to modify certain things based on our new model, but forgot that the radiation constant itself is modified because of the variation of the constants. And he did not take that, they did not take that into account, the two authors. So this is one of the reasons we have to do work very, very carefully. It is very easy to prove something wrong because you have not done it properly. If you don't do, you want to falsify something, and you will falsify if you don't do it correctly.
Mm-hmm. Do you have in addition to vocal critics, do you have a lot of supporters that are working with you?
Yes, I do. I do have few, not a lot of people, but I'm trying to make, this is where the podcast like yours come into play. Very important, because the people have to understand that things of this magnitude cannot happen in isolation. We want other people to think in unbiased way. If the theory proves to be incorrect, let it be. If it is wrong, most of the theories are proven wrong after initial excitement. There is nothing wrong with that. But at the same time, if something is proven wrong because it's not applied properly, that will be a lost opportunity.
Indeed.
So this is my thing, is that let's try to work together. Let some people be interested. However, I do understand people have limited time and they have to produce paper or produce work within whatever time frame they have spare. So they can't put a lot of time understanding it. I'm finding I have two postdocs now working with me remotely. They should join me pretty soon. But I'm finding it so difficult for them to understand what the theory is. They're trying to just understand part of it, apply it quickly, and produce the result for me. And they are, because we are working at this point remotely before they move to Ottawa. Here, I'm I'm having a lot of difficult time to make them really understand how to apply it correctly, this theory.
Are you searching for grad students right now?
No, unfortunately, we don't have a graduate program at the University of Ottawa. They don't award PhD degree in here, but they do. Postdocs don't have to be awarded degree, so I can hire postdocs, but I cannot hire graduate students.
I see. I mean, I'm glad that you're finding people to work with, and if there's anybody in the audience who is maybe interested, who is a postdoc, what's the best way for them to reach you?
Oh, they just write to me at my email, which is rgupta4@uottawa.ca.
Okay, well, I hope that somebody reaches out.
Yeah, I'm really excited to get you back here to
just
talk about these cosmic filaments too at some point. That's something I'm really, really interested in.
Yeah, I hope we have some. I would want to talk when we have some real results.
That's fine. We'll be here all day.
Yeah, I know.
Be here. We'll be here when you're ready.
That's right. If somebody didn't get my contact, they can just go and see University of Ottawa, my name, Gupta, or R. Gupta, and you will be able to find me on the web there, and you can then contact me. You will have email address, phone number, everything there.
Excellent.
Yeah. Well, best of luck. Yeah, I'm really excited to keep seeing you pop up in the news, and I'm glad you were on Brian's show, and I hope you do more podcasts, and yeah, just kind of fertilize the change. I think really just keep people excited that there's work to be done. There's too many kids, I think, who go through basic physics courses and feel like it's all nailed down and figured out. And so I appreciate your work, appreciate what you're doing out here, and thanks for coming and sharing your ideas with us.
Thank you very much for giving me again the opportunity to be on your show. It's very nice to be able to talk to you, and I learned a lot of things from you as well. It's
Oh.
very good.
Appreciate
Thank you
that.
very much.
Our pleasure. Thank you
All
so
right,
much.
let's do it again once you get a little more work
another
done.
time.
Okay.
I'll inform you when I have something to report.
Excellent.
Perfect.
Okay.
All right,
Thank you.
take care.
Bye bye now.
Have a great rest
Take
of your
care.
day.
Bye bye. Bye
Bye,
bye.
everybody.